MacuHealth is a nutritional supplement leader. Our targeted formulas include MacuHealth for daily eye health, MacuHealth Plus for aging eye support, Vitreous Health for vitreous care, Vision Edge Pro for visual performance in athletes, TG Omega-3 for ocular and systemic wellness, and MacuHealth DM for eye and metabolic support. Call MacuHealth today and mention this podcast for special discounts. Experience the difference with MacuHealth. Nutrition you can see.
With more screen usage and indoor time, myopia, also known as nearsightedness, is increasing and getting worse in children. Now, certified eye doctors can prescribe MiSight One Day, the first and only FDA-approved soft contact lens to slow myopia progression in age-appropriate children. Visit CooperVision.com to find a Brilliant Futures certified eye doctor near you. Do your patients know what presbyopia is?
There are people who are afraid of the press.
Have you talked to your patients about multifocal contact lenses?
I've heard the bifocal, but not multifocal.
Do you need help with your multifocal strategy? Learn more at the conclusion of this episode. Welcome back to part 2 of my conversation with Dr. Andrew Salzman. In this episode, Dr. Salzman reveals how NAD supports healthy blood pressure and plays a surprising role in building muscle. So let's dive in. If you're new here and you like our interviews, press like, subscribe, share, and hit the bell. Also, please leave comments. Be sure to watch our full-length documentary, Open Your Eyes, on Amazon Prime, Apple TV, iTunes, Google Play, and YouTube Movies and Shows. Let's talk about, before we go into the product, I want to talk about lifestyle factors that lower NAD: poor sleep, sedentary lifestyle, stress, refined carbohydrates, eating a processed food diet, low protein, not having enough tryptophan. Is that some overeating, chronic overeating? Are these things that you agree with that are lifestyle factors that lower NAD?
There are a lot of lifestyle factors that are important here. Let's start with diet. Where does NAD come from? I mean, some of it we salvage and we reuse. There are salvage pathways, but at the end of the day, we have to eat the precursors for it, or we can't make it. The major precursor is tryptophan. It's an amino acid. Where does tryptophan come from? It comes from food. Certain foods much more than others. Milk, fish, broccoli, a little bit in tomato, cheese. There's certain foods which have a good amount, not a lot like the supplements that we're giving, but they have a decent amount. And a good proper diet in these particular foods provides that precursor, that important tryptophan precursor. So diet is something we cannot ignore. Second issue would be exercise. When you truly exercise, I'm talking about not just walking across the room, but if you're doing cardiac exercise, that causes stress in a good way. It causes hypoxic stress in the muscles, and the muscles respond to that by making more mitochondria and by increasing in those mitochondria the ability to generate NAD. So the factory that makes NAD, that salvages it or recycles it, or that even takes the precursor from our food, the tryptophan, this is dependent on mitochondria to a large extent. Exercise increases, it induces, it instigates a huge expansion in mitochondria. If you, for example, look at a professional basketball player, they can go out for 60 minutes, play like crazy. I could never do this. I mean, they're out there and they're running and they're not even out of breath. Why is that? If you look at their mitochondria, if you look at their muscles, their heart, their skeletal muscles, they're loaded, they're packed with new mitochondria. And that produces NAD. So a basketball player can produce an enormous amount of NAD per minute, far more than any of us who are more sedentary can. So exercise is a critical component, in my judgment, in maintaining good NAD levels. And people who are, in general, much more fit live longer. I mean, it's not always. I mean, you can have bad luck, but certainly being in incredibly good shape is a major factor in your endurance and your ability to live longer because of that.
As we get older, can we make more or new mitochondria?
Oh, yes. Yes. But not to the same extent. Like if you take an 80-year-old man who's weightlifting, and you look at their muscles under a microscope, you'll be very impressed. I mean, they'll have a very good number. But if you take the same man when he was 15 who was weightlifting, they're a lot more. So there is over time a senescence. There is a decrement in your ability to be vigorous, and no 80-year-old can outrun a 20-year-old. Okay, even if they're working out and even if they're running and all of that. But yes, you can have a major difference. That there are 80-year-olds who run the Boston Marathon. So you can have a pretty darn good level, but it's just not peak level.
And how does NAD relate to VO2 max?
Okay, well, so VO2 max is the measure of the consumption of oxygen in a cell or a tissue or an organ, right? So the ability to use oxygen has to do with your ability, first of all, to breathe it in. You have to have the supply. So VO2, consumption of oxygen, is dependent on DO2, on the delivery. You have to get the oxygen by having good lungs and being able to breathe well. Okay, and you have to have hemoglobin in your blood, good blood cell number to carry it there. So that's the DO2, the delivery. But then the VO2 on its own is dependent on how well you can reduce oxygen, how well you can bring electrons to oxygen to reduce it, to form water and to form CO2. And that depends on the energetic pathways. The major energetic pathway, there are three in the cell. There's first glycolysis, where you break down sugar. Then there's the Krebs cycle inside your cell, where you're producing some NAD and a little bit of ATP. But then the fundamental driver of ATP production is the electron transport chain. That's the last stage, the three stages of energy production: glycolysis, Krebs cycle, and electron transport. And that last stage, you're passing an electron down the chain from NAD, by the way, and ultimately that electron finds oxygen at the very end, and it grabs onto the oxygen and it reduces it. Okay, so it's forming water. And so that's the end. That's the end goal. So if you are able to have the NAD there that you need, you will have more electrons to donate into the electron transport chain, and therefore oxygen will be consumed, and that's VO2, that's the consumption. So NAD is a direct requirement for having enough NAD is a direct requirement for being able to consume and use oxygen for VO2.
There's been some suggestion that if you're exercising and you actually cut your oxygen off a little bit and wearing like bands in your arms and doing exercise, that you could drive more mitochondria. If you believe there's anything to that, and that NAD helps to drive mitochondria when you're actually cutting off some of the oxygen during some of the exercises.
You're correct in principle, but you don't need to do that. When you go out and you exercise vigorously, and I mean really run, really lift a lot of weight, really swim, you don't need bands. You are creating in that tissue relative hypoxia. The tissues are not getting enough oxygen because you're stressing everything to the max. If you try to run, say, 20 miles or 10, if you just pour out your effort, your muscles will never have quite enough. In fact, even elite runners will get cramps. And the reason they get cramps is because during glycolysis, because during the energy production, they don't have enough oxygen, they don't have enough NAD, they don't have enough, and therefore they get fermentation of sugar, and that's producing lactic acid, and that's why you get cramps. That's why runners get cramps. They are exceeding their ability to produce ATP through oxygen consumption. They're going over the limit, and that's a good thing because that is a stimulus to your body to produce mitochondria. The more you exercise at a peak level and you really push yourself, the more you're stressing your muscles with hypoxia, with lack of oxygen, and the more the muscles will respond by biogenesis of mitochondria. They will make new mitochondria. And that's why a basketball player, professional player, they have just loaded with mitochondria, or a professional runner, a jogger, loaded with it. And they've done that through hypoxia. You don't need to squeeze the muscle with a rubber band or a belt. You just need to run. That will produce all the hypoxia you need.
So that fad I see in the gym, some of these guys doing is not necessary.
No, they just need to do a few more reps. They'll get there. Yeah.
So I want to ask you also about a heart attack. With the role of NAD and somebody dying from a heart attack and not dying because of lack of NAD.
This was my field. This is what we actually, if I can say that this is where we contributed the most. This is what actually happened. We in 1994, I formed the I founded the Division of Critical Care Medicine at Children's Hospital in Cincinnati. Built a very large ICU, and we had a research group that was focused on the question you have just posed here. And we asked ourselves, what happens when you have a coronary artery that's blocked or a blood vessel in your brain that's, you have a stroke? What exactly happens in the seconds after that? So we measured it, and it was quite interesting. When you block a coronary vessel, this is what happens in a heart attack. You have three big blood vessels in your heart, coronary arteries, and if you block them, there's ischemia. There's not enough oxygen going to the heart tissue, to the muscle. So in the first few seconds, you have oxidant deprivation, but also oxidant stress. You start to form what's called singlet oxygen. You form hydrogen peroxide and you form peroxynitrite. This is within about 5 to 10 seconds. And what they do, among other things, is they are very lipophilic. They can cross membranes super fast, and they go right into the nucleus within about 3 to 4 seconds, and they attack your DNA. Incredibly so. And they cause nicks. Remember, I talked about how DNA is a double strand, it's this helix. Well, these oxidants come down like hydrogen peroxide and peroxynitrite, and they slice open one of the strands, not both, but one. And the entire genome, the entire DNA that you have within about half a minute is littered with hundreds, even thousands of these nicks everywhere. Well, PARP is an enormous protein in the nucleus. It's everywhere. And it is, it's like the alarm bells go off. I mean, it's seeing these everywhere, and it grabs all of them all at once. Every PARP in your nucleus is recruited within about a half a minute to a minute. They're recruited right onto all these breaks. Okay. What does PARP do when it's activated? It looks for NAD. That's how it works. So NAD grabs onto the PARP everywhere, and the PARP's everywhere, and it starts cutting it to make these long chains, these long polymers called poly-ADP ribose. The NAD levels by 2 minutes are near zero. I don't mean low, I mean zero, literally zero. Without NAD, how do you make ATP? You need NAD for ATP. You need it in glycolysis, the Krebs cycle, and the electron transport chain. We talked about those 3 stages. So at 3 to 4 minutes, the ATP levels go to zero. So here's the progression. The heart gets blocked, the blood vessel, no oxygen. Within 1 minute, oxidants are formed. Within 2 minutes, they attack all the DNA and you get nicks. Around 2.5, 3 minutes, PARP is activated like crazy. By 4 minutes, NAD is gone. By 5 minutes, ATP is gone. Well, in the absence of ATP in your brain or your heart, you get what's called necrosis. This is not apoptosis. This is a situation where the cell literally gives it up. It's dead. The whole cell falls apart. The membrane breaks open. Everything is ruptured. It's dead. It's necrotic. And that is called a heart attack. And if you go out 15 minutes or 20 minutes, half an hour, that those dead cells accumulate, and you actually see in your eyes, you see white, dead tissue in the heart or the brain. If you have a heart attack or a stroke, you can't recover from that. Once it's dead, you've lost, a part of your heart or your brain. Now imagine if you were to use a lot of glutathione. So you had a lot of glutathione there. It could buffer for a while all those oxidants in minute 1, up to a point. If you had no glutathione or very low levels of glutathione, this whole thing shifts to the left. It's much faster. Someone with low glutathione, because he has a lot of oxidant stress, when he gets an interruption in his blood flow, everything I said is even faster. Okay, what happens if you have no PARP? Imagine that. You get the oxidants, you damage the DNA, but where's the PARP? It's not there. Or if it is there and you block it with an inhibitor, it binds to the nick, but it can't bring an NAD now to attach to it. So the NAD levels are high, they're sustained. Even in the face of all of this genetic injury and PARP activation, the NAD levels don't fall. What would happen? ATP would be okay, NAD would be okay, the heart would not die. It wouldn't get damaged in the brain from a stroke. So we did that. So we created these PARP inhibitors, which were incredibly powerful, and we could shut it down. And then we gave animals heart attacks and strokes experimentally. Their heart was okay. The brain was okay. And this was at the very basis of the Genentech license, because we had large animal studies in large, pigs, big animals. We would block their coronary artery. We expected a big infarction there, but we gave the PARP inhibitor as quickly as possible. The heart was okay. It was amazing. So in this instance, what does it tell you? NAD, very important. If you can maintain and sustain NAD levels in the acute setting, and I was an intensive care specialist for kids, so I cared about acute settings. I wasn't treating chronic disease and aging at that point in my life. I was worried about 5 minutes, what happens. So this was the reason I developed and was excited about creating something that could maintain NAD even in that setting and save lives.
So are hospitals using this to help prevent heart attacks? And if they're not, why aren't they using it?
Well, that's a very good question. I wish I had the answer. I guess because they really focused on these oral drugs, for breast cancer, for BRCA deficiency. But what they really needed was the drug that we had, which was IV, which you could give it right away. I don't know why they're not doing that. I think the cancer market is enormous for them, and it's very effective, and it's approved by the FDA, so they've gone with that. But there's a tremendous opportunity to save lives by blocking PARP in these acute settings, and the drugs are out there now.
Like people recommend chewing an aspirin if you're having a heart attack. As soon as the ambulance comes, the first thing they do is they give you an aspirin. How about a PARP inhibitor to chew as well?
We did those studies in animals extensively, dozens and dozens of studies like this. The results are incredible. They're in the literature. They're really what is needed is a company not in the cancer space who will see this as a threat or competition to them, but somebody in the cardiovascular space who can then harvest the technologies, maybe they're off patent, for example, and then deliver them into an IV formulation because it needs to be given fast. When you swallow a drug orally like Tylenol or Advil, it takes about 20 to 30 minutes to be absorbed by your intestine and to get into your blood. For a heart attack and stroke, time is of the essence. You need to get something in there within 1 minute. And to date, none of these have been formulated for IV use. So that's, an impediment. It could be done. It's not impossible to do.
But if you're chewing an aspirin, doesn't it happen quicker than 20 minutes? You're home, you're getting the jaw pain. Not really, huh? You couldn't do that with a
No,
PARP inhibitor, a cherry flavored PARP inhibitor to chew it.
I like that idea, actually. Let me think about that. That's very good. A sublingual, like a nitrate or something.
Yeah.
Yeah, that's actually a very clever idea. Thank you. Good
So,
thought.
so let's get in. Oh, one more before we get into the product. Vulnerable plaque for heart attacks. That's what we worry about, obviously. More than constriction, we're worried about vulnerable plaque breaking off. Is there anything by having proper NAD levels that could prevent vulnerable plaques from rupturing?
Well, having a proper nitric oxide on the endothelium of the blood vessels is critical for the development of plaque and preventing spasm of the blood vessel and preventing disruption. The whole maintenance of the endothelium is tied in to proper nitric oxide levels. And so nitric oxide deficiency or relative deficiency, which is completely a result of falling NAD levels and NAD pH, would make a difference, I believe. So yes, I think having good NAD levels would certainly maintain the endothelium. There's actually been a publication in Nature in humans where they gave NMN supplements. These are precursors of of NAD, and they lower their blood pressure. So certainly it has been proven that the endothelium, the inside layer of the blood vessels, which is critical for plaque formation and disruption, that can be maintained and kept healthy through NMN supplements.
So I'm very interested in how we could raise NAD and taking proper supplements. It's a big fad now in these IV clinics that they're doing IV NAD. You have to sit there for like 2 hours, I think. And I heard my understanding, it's not very comfortable. And they're doing this, they're doing these IV NADs, or the people are doing sub-Q injections at the house to raise NAD. But is that really getting into the cell where we need it, or is it just going into the blood? The when they're doing the NAD IV or the sub-Q, because we got to get
Yeah,
it into the cells.
you're entirely correct. The NAD molecule has two features going against it, which prevent it from traversing from the blood into the cell. Number one, it's big. And number two, it's very polar and charged. It's got a negative charge on it. So it doesn't go across cell membranes. If it's outside the cell, it won't go into the cell. If it's inside the cell, it won't cross back to go outside the cell. Why is that important? There's a huge investment by the body in making NAD. It's a really important molecule. It's important in hundreds of reactions. It takes a lot of work to make NAD. You need to have food, you need to have oxygen, you need to have all this complex machinery. Imagine you make all of this, you go to all this trouble, the cell makes NAD, and 2 seconds later, it falls out of the cell and is useless. Doesn't make sense. So the body evolved in a way that NAD is trapped inside the cell. Return on investment. You want to invest something, you don't want to lose it. If you have a bank account, you don't want to see the money go out the window of the bank. Same concept here. The problem is if you swallow NAD or you take an IV, it will get near the cell, but it can't cross into the cell. So it's useless. So taking NAD per se is not very wise. It doesn't really do anything. There are other forms, though, that are precursors that can cross into the cell, specifically shorter versions of NAD. The next shorter version is called NMN, and there's an even shorter version called NR. These are tiny. They're small. They're not as charged. NR, for example, is not really charged much at all compared to NMN or NAD. And there are also special proteins or shuttles, think of them as tunnels, that the cell has, that it's designed into the cell, that short circuit, it allows NMN or NR that's outside in the blood to be pulled through right across inside the cell. Unlike NAD, it doesn't work for NAD, but these smaller molecules, they can just pull them right into the cell. When they get in the cell, there are enzymes there that create NAD. So for example, you have NR, which is nicotinamide riboside, to sugar, and you want to make it into NMN. So you add a phosphate with a kinase. It's called NR kinase. It makes NMN. And then there's another enzyme in the cell which takes NMN and is called NAMT2, and that adds an adenyl transferase. It adds the last part. Now you have NAD. So these guys who are taking NAD at home, or they go to a clinic and they get an IV,
Very
which by the way
expensive.
is not
Very expensive.
and expensive and also not much fun. If you've had IVs, they're not something that you enjoy getting. They hurt like the deck. I mean, they're very painful. I used to put them in for a living. No one enjoyed that. They don't give you a tip for putting an IV. So when you fill your blood up with this NAD, it's just all circulating, but it can't get in there. What can you do? You can take precursors. So what precursors can you take? Well, you can take two NR and NMN. You can take them orally. You can swallow them. They go into your body. You swallow them into your stomach. They go into your intestine, and they cross over into the blood, and they circulate. They go by the cells. They see those tunnels. They slip right in. and then the cells convert it to NAD. And if you do that, if you give someone a pill like that, and then you measure the NAD in their cells, it goes up. It works. The concept works.
And so in your product, you not only do you have NMR, but you have things to block the problems. So you added resveratrol that will degrade the CD38. So talk about your product. You put NMN in it, a 900 milligrams with 2 capsules. And now
Yep.
we have other things that we've added. We know why it's important to the NMN to make the NAD, but we don't want to lose it. So now we add resveratrol to degrade the CD38. So talk about resveratrol, why you pick resveratrol, and how much resveratrol you picked.
Well, resveratrol and there's also another element in there called hydroxytyrosol. And those are all in this mixture that we produce there. And when the resveratrol actually has three functions. First, it's an antioxidant in and of itself, which is a great thing, removes oxidant stress. Number two, it actually increases the production of the enzymes that make NAD from tryptophan, which is nice. That's another function that's independent. And then lastly, it has a negative effect on CD38 expression. So it's lowering the levels of CD38. That, along with hydroxytyrosol, is also doing that. So you lower the levels of CD38, maybe not back to normal, but you lower them down. So now you have a situation where you have more NAD being produced because you're giving an NMN supplementation, and you're blocking the cleavage. By interfering with CD38, you're blocking the cleavage of the NAD. So that's why we made a combination. And I really believe that this is really going to become important. There are a lot of companies out there who are approaching this by just giving a lot of shoveling in a supplement, the precursor. And that's okay. I mean, they will see a bump, an increase in NAD. That's been shown. But how well is that sustained is the question. And for that, I think, as I mentioned before, CD38 is so exciting and so important because it removes NAD that you really need to have some type of a blocker. And we're constantly doing research in our laboratories to look for other natural ingredients that block CD38, thinking about new products like that. We really feel that the combination here is much more critical and more successful than just giving a supplement per se.
We're up against a break, but don't go anywhere. We'll be right back with Dr. Andrew Salzman.
MacuHealth, your science-born and tested solutions for visual performance, macular degeneration, and dry eye syndrome. New products coming soon. Embrace the science.
Why did you pick resveratrol, not quercetin or luteolin, to help, pomegranate extract? These are all things that block CD38. Why did you pick that as opposed to quercetin, luteolin, or say pomegranate extract?
Well, I think because of the other two features of resveratrol. Resveratrol is sort of a handyman who can do all kinds of things. It's a relatively good antioxidant. Not that quercetin's too bad either, but resveratrol is a darn good antioxidant. And then, as I mentioned, it also has been shown to increase the enzyme levels that make NAD from tryptophan. So it really was doing triple duty. So we thought that's pretty cool. We should include that. It's very useful. Hydroxytyrosol, the data are less strong for having that.
Explain what hydroxytyrosol, where it comes from olive trees. So that's the next ingredient that you have in there. Explain that from the beginning. Thanks.
Well, the Mediterranean diet has been shown to be very successful. I mean, people in the Mediterranean seem to live longer. They have less cardiac problems. There are a lot of positive things you can say about that diet, and they seem to put olive oil in everything. And when you start looking at all of the different cultivars from olive trees, and there are many different cultivars, not just one type of tree, it seems that hydroxytyrosol is one of the key things that's been associated with good outcomes. So people have then purified it and ultimately studied it. And it's been found to be a good antioxidant. And it's been found to also, as I said, influence the CD38. And so more and more people are recognizing the importance of some of these, not just olive oil extracts, because there's a lot of stuff in there that's not so important, a lot of flavonoids that are not really critical, but some of the key things in the olive oil, and hydroxytyrosol would be right, I think, at the top, are really being recognized for their roles here. So we included that, and that was to help the resveratrol. We think the combination of those three altogether is actually very important. We also have a fourth molecule in there, which is ergothioneine, which is a very interesting amino acid. It's natural and it's a powerful antioxidant, different type of antioxidant. So we actually have 3 antioxidants plus NMN in there. And we think that that combination is what makes the difference with our product.
And what does ergothioneine do to PARP?
It doesn't have a direct connection to PARP, but it has an indirect connection because it is an antioxidant that's quite potent, gets into the cells. There's a specific receptor uptake for it. So you can get high levels in there, and it will fight off the oxidant stress and reduce DNA damage. And by reducing DNA damage, you don't activate PARP, and therefore you don't consume NAD.
You know, NF-kappa beta is a fascinating molecule within our body because when that turns on, that's what causes the cytokine storm. Everything, all the inflammatory gets turned on. Explain how what NAD does with NF-kappa beta and how it may kind of tamp it a little bit.
That's an interesting question. NF-kappa beta is activated in 2 ways. One is by oxidant stress. We were actually the first to publish on that in 1997. It was a very important paper that we did called oxyradical signaling that activated NF-kappa B. And the other thing that turns on NF-kappa B are cytokines. Okay, so they cause activation through NF-kappa B is a critical signaling molecule that's governed by another molecule called I-kappa B. And then when that's phosphorylated, it falls off NF-kappa B, and NF-kappa B rushes to the nucleus and upregulates the expression of all these things that you mentioned. You get the cytokine storm and sepsis and so forth. And NAD is not, we don't have data yet to show how NAD is blocking NF-kappa B, but it appears to be doing that. We did experiments, for example, where we gave NMN to monocytes, which are the white blood cells that are circulating in humans, which human monocytes. And we showed that we could block with NMN production of a cytokine, IL-6, which is NF-kappa B dependent. And so in some way, which we don't quite understand yet, the NAD is slowing down or blocking NF-kappa B activation. It's a phenomenon. We don't know how it's doing it, but in some way, it must be regulating the upstream events. The upstream event for NF-kappa B, as I said, is I-kappa B. And in some way, NAD must be interfacing with the phosphorylation and degradation of I-kappa B, which is an inhibitor of NF-kappa B. That's an ongoing area of research that I'm very interested in, but we haven't figured out yet how that's happening.
So you have NMN in your product. How come you didn't put NR and NMN in it, even though NR turns into NMN?
That's a really important question for a different reason. It turns out that NR, for reasons that are still under investigation, that NR actually does 2 things. On the one hand, it clearly can become NMN and NAD. I talked to you about that. Okay, so it's a supplement, but it turns out that it also has another unexpected role, which we're learning about right now. NR is able to bind to CD38. We actually know the amino acid that it binds to. It's glutamic acid 266. It binds to this. And not only does it bind to it, but it actually covalently links to it and won't come off. It's like the plumber who comes and will never leave. It will not leave. And it inactivates CD38. It actually kills it. So surprisingly, NR is an inhibitor. We call it a suicide inhibitor because it won't come off and it kills the enzyme. It's a fascinating molecule. And it then poisons the CD38 forever. You have to make the cell has to make new CD38 to recover. It's out with stuff. So that is something that NR can do. NMN does not do that. NAD does not do that, but NR does. We don't, and we know that it happens. We don't know exactly the biochemistry of why that's happening, but it's clear that it's covalently bonding. So one of the thoughts we had in the future is to start to add NR into our products in a way to serve that function. The NMN per se is sufficient for, oh, I've lost you.
No, I'm here.
Oh, you're still there. Sorry. Okay. The NR per se is a great donor, but it's not as good as NMN. NMN is the quintessential way to drive that into the cell. But we may start adding NR to that in order to augment that and to block the function of CD38, in addition to resveratrol and hydroxytyrosol.
I mean, it would make sense to me. I mean, of course, it'll make the product more expensive, but it does make sense. I know like Life Extension sells an NR product. Uh,
Yeah.
how about like some of the foods that block CD38, like chamomile tea, parsley, uh, you know, oregano, some spices, celery, cabbage. Do you recommend people eat that? Those are healthy things anyway.
I mean, I don't have a problem with people eating them, but I think the jury is out about how efficacious they will be in suppressing CD38 activity. I think it'll be rather weak. I think that really a potent CD38 inhibitor ultimately is our goal. We're surveying a number of natural products right now that will be CD30, more effective in CD38. Ultimately, our goal would be to have a very powerful CD38 inhibitor.
Are there any medications or drugs that inhibit CD38?
Yes, there are some monoclonal antibodies. There are two monoclonal antibodies that have been created for treatment of cancer. As you started off by talking about multiple myeloma and how it has high levels of CD38. So there are two monoclonals that have been produced that effectively interact and inhibit that. They're not used and they're not relevant to this discussion, but they're out there. And there are also a couple molecules that have been made through high throughput screening to block CD38. Those were made with the intention of being for cancer, but actually one could think of them as being very effective for sustaining life, for longevity. And so we are also, I should mention, at Wonderfeel, the company where I'm the chief medical officer, we have an active chemistry program to create novel, potent CD38 inhibitors. We will be using them either as supplements in our new products, or ultimately we may transition and also enter the pharmaceutical space with them.
Why do you put vitamin D in your product? Vitamin D3, about 800 IUs of vitamin D if you take the two capsules. Because a lot of people take vitamin D anyway. So why put that in your product?
That was a historical reason. We started off with that 5 years ago. We thought it would have some other properties that we thought would be important for longevity. There was some data at the time, but it's not, it's really more a vestigial addition that was originally in the product, and it's not really the main driver of the product.
And is it something that you would consider taking out or
In the future, it's not going to become a critical part of our new program.
and I assume the best time to take the product is in the morning. I don't want to take it before you go to sleep. And do you
Right.
take it with food or can you take it on an empty stomach? What's the best way to take it?
You can take it on an empty stomach. We recommend that people take it first thing in the morning because your activity level, of course, rises when you're awake. When you're sleeping, your requirements for NAD are much less. So the best time to boost up your levels would be when you're most active during the day. So we recommend that people put it next to their toothbrush. Don't forget it. Take it first thing in the morning. They can take it on an empty stomach if they wish. And then they have it there during the peak period in the morning and early afternoon when they're most active.
And I think you kind of alluded to this before, but NR versus NMN. NMN has a shuttle mechanism, which NR doesn't. Can you talk about that?
Well, NMN is NR with a phosphate on it, so it's much more charged. It's electrically negative, very polar, very water soluble, and it does not like to cross lipid membranes. You cannot push NMN into a cell. So these specific shuttles are vital, and they're effective. So they can get NMN into cells very, very quickly. NR doesn't have that same shuttle. It's less negatively charged. It has a free OH group, a free hydroxyl group, but not a phosphate. So it's much less negatively charged. It's polar, but not to the same extent. So that can get into cells to a certain extent. But NMN has a specific shuttle. It has to. Otherwise, it could not possibly enter the cell. And that shuttle accelerates the entry. And so that's why that was the real driver in our thinking. Why NMN and not NR? I don't want to disparage NR though. I mean, there are data showing that NR supplementation does lead to NAD increases. It's not a bad drug, and it has that suicide inhibition effect on CD38 I mentioned. So I don't want in any way be disparaging about it. It's something that we're looking at very carefully for future products, and it's probably a good idea, but it would need to be given in a special way to optimize its effect in terms of dosage and in terms of what it's given together with. It's not just as simple as giving NR.
How long do people have to take it before they feel an effect? You know, obviously, if you're a professional basketball player and you're already at max, you may not feel an effect like a regular person who's depleted in NAD. But how long
Yeah.
on average, would you say, from looking at people who bought the product, who talk about it, how long is it usually for them to feel an effect?
Well, a lot of these chronic diseases that we're talking about here, or even energy from muscle activity and so forth, it takes a while to recover and rebuild, to build up your mitochondria, to deal with some of these chronic problems. So it's not something that's going to be present in a day or a week. We usually think 3 to 4 weeks is about right, and that's what the feedback we've gotten uh, from our customers through the registry we keep. We have people report back to us how they experience the product, and we're generally seeing about 3 to 4 weeks before something is impressive enough for them to write us about it.
Well, I could say I've been taking it for maybe 10 days and it's really helped my sleep. So I want to talk about NAD and sleep. And
Yeah.
sleep is so interesting. Uh, if you could talk about what happens with sleep and NAD and ATP and how that all works.
Well, sleep, of course, a third of our life is when we're asleep, and it's a critical process because during the day, every event in the brain that is happening is highly energy requiring. I mentioned that the brain is getting 25% of our blood supply. It's one of the largest consumers of oxygen, tremendous amount of metabolic demand in the brain. And the ATP that's used in the brain, it's for all of the thinking, all of these neural transmission, when it's used, it's broken to form ADP. And then the ADP is broken to form AMP, and then the AMP is broken down to form adenosine. So the brain uses as much of the ATP as it possibly can to squeeze out every last bit of energy that is there and is available. So at the end of the day, with all of this thought process going on, you're producing more and more and more and more of adenosine at the end, right? Because ATP, ADP, AMP, adenosine, and the brain starts to fill up with adenosine. So by 8 or 9 or 10 o'clock at night, your brain is chock full of adenosine. And the body is very clever in that it has created a way for you to know that, to change your behavior, and it's called being tired. So being tired is an evolutionary adaptation that translates or communicates adenosine excess and tells you go to sleep. So when you go to sleep, which you will do, when adenosine levels rise high enough, you will go to sleep no matter what. You can try to stay up, but eventually the adenosine will overwhelm you. You can't drive a car. You will fall asleep. And then when you go to sleep, the adenosine is used back up with NAD, and it's rebuilt to form ATP through the use of NAD while you're sleeping. When you wake up, hopefully, if you've had a good night's sleep, you have now converted all the adenosine back with the help of NAD back to ATP, and you're ready for another day. Many people, though, decide to get up early. Maybe they have to go to work. Maybe there's a reason. So they still have adenosine floating around. That's a problem. That means when they get up, they're still tired and sluggish. How are they going to go to work? So most Americans, faced with that situation, take an adenosine inhibitor in the morning. 95% of Americans take adenosine inhibitors in the morning, which is caffeine, coffee. Once they take 1 cup of black coffee, the caffeine that goes in blocks the adenosine receptor. So you can still have adenosine in your brain. You didn't get enough sleep. You can't cheat Mother Nature. I mean, you did not sleep long enough, which is bad. But they have to go to work or whatever. So they take coffee, they block the effect of adenosine, and they trick the body into thinking that it had a good night's sleep and that it's had enough adenosine, had enough time, and people are awake and alert. But it's not healthy. The better course of action, of course, is to sleep enough and let the adenosine be recovered, not to drink coffee.
See, I understand why NAD gives you energy when you wake up because it helps build ATP. But I don't understand how it helps you sleep better, because it's helping me sleep better because it's building.
It helps the conversion. Well, the conversion of adenosine back up to ATP is building up your energy. That's using mitochondria. That's oxidative phosphorylation using oxygen and NAD. That's how the adenosine is recovered. The actual sleep, the function of sleep, is to reverse adenosine back to ATP with NAD. NAD is crucial. It is the driver of sleep recovery.
How about for people that wake up in the middle of the night, they sleep for a couple hours and then they can't stay asleep? Any tricks for that?
That's really outside. Insomnia is not really related to NAD levels. That would be something else that altogether. So NAD wouldn't have a role in insomnia prevention or treatment.
And I noticed that some companies are putting adenosine in their supplement to help people sleep. How do you feel about that?
Well, it will work. I mean, yes, if you want to load up on adenosine. The problem with adenosine, and I know something about adenosine because I developed the first adenosine receptor 1, adenosine type 1 agonist for glaucoma. In fact, our company went onto the NASDAQ for that discovery. So adenosine has 4 receptors that it binds to: A1, A3, A2B, and A3. And so when you give someone adenosine, you are activating those 4 receptors, and there are all kinds of effects that you don't want to get involved in with those 4 receptors. It is not healthy to be loading up on adenosine like that. There are a lot of side effects that will happen. I mean, you can lower your body temperature, you can have all kinds of changes in your ability to fight infection, your eye pressure changes, many things going on. So taking adenosine, not to mention effects on your heart, it can slow down your heart rhythm. You take enough adenosine, it will stop your heart. It's used to treat supraventricular tachyarrhythmias. So taking adenosine, a lot of adenosine, not a great idea.
So talk to me about what glaucoma, what happened, and I guess the product never came to market, but did it lower the pressure, and how did it actually work?
We had an adenosine 1 receptor agonist called travadenosine, and that went through phase 1, 2, and 3 clinical trials, and it was quite effective. And the reason it didn't go into the market after that was that the competitor, which was latanoprost, it's a prostaglandin, had just come off patent. And so the prices plummeted. It was very cheap. And so strictly from a pricing standpoint, our product, which was new and expensive, of course, a new drug, was priced too high above the generic latanoprost. Even though latanoprost had many side effects, which our product did not have. Latanoprost is not a lovely cure for glaucoma. There are a lot of side effects. But, it was cheap. People use it and so forth.
And how much did it lower the pressure?
Our drug.
Did it work as good as latanoprost?
It worked as well as latanoprost, yes.
Interesting. Wow, very interesting. As we finish up, any other things now switch to the eye since we talked about it, about the eye that you didn't cover that you would like to cover for our audience? Because we have a lot of eye doctors that listen to this, optometry students, ophthalmologists, optometrists.
I think NAD is going to be a major area of eye care in the next 10 years because it influences the cornea. It can prevent keratitis. It increases tear formation. It probably will be effective in glutathione production and preserve the lens longer before cataracts form. It's been shown to be effective in animals for diabetic retinopathy in terms of preserving photoreceptors and preventing retinal detachment. It's been shown to reverse acute macular degeneration in mouse models of that disease. It's even been shown very impressively to reduce retinal injury after ischemia reperfusion of the retina in mice. So there are numerous ocular diseases in which NAD supplementation has been shown to be effective in mice. And more than that, in those animal models, when you measure NAD levels in these tissues, and CD38 especially, you can see that the retina is an incredibly important organ, very sensitive to all of these insults, and definitely part of the aging process. The retina, as we get older, unfortunately, is not like it was when we were kids. And although we're not aware of it, but our vision is debilitated as we age, very much so. So I think there's a tremendous opportunity. The goal for ophthalmologists and optometrists going forward is, how do you get it there? Do you take a pill and just, do you take a pill for your whole body, but focus on the eye? Maybe that could be. Can you give it as an eye drop? There are data showing NMN eye drops are effective on the anterior chamber of the eye. Okay. So there's a lot of opportunity in the eye space. I hope to be part of that opportunity. We're looking at that in the company, and I think it's a really exciting place for the future for this field.
I mean, Americans' number one fear is blindness. It's not cancer. It's blindness. And you mentioned latanoprost before. I have, 500 active glaucoma patients. Just me personally, I don't have a lot of side effects from latanoprost. There are some, the eyelashes grow, their eyes go, but it's not too bad. But of course, we would love to have extra medications to lower the temperature, because nothing works for everybody. A lot of people have to be on multiple medications. But this is a fabulous discussion, Dr. Salzman. You're really something. You're an encyclopedia. People want to find out more about you, about Wonderfeel, contribute somehow, take the product and give you feedback. How could they do that?
Well, we have a website. There's an address there where you can contact us. And every customer we have is an important customer. We learn from our customers. We listen to them. Their feedback is essential. In fact, we invite feedback because it forms the registry, and we've just had a paper now accepted based on comments from our customers. So we are very excited for your feedback and to learn from you.
Well, I could say that Wonderfeel is very lucky to have you. You're a brilliant scientist, a very nice man, and I want to thank you for sharing this great information with my audience. Dr. Salzman,
thank you
so much.
Thank you. Take care. Bye.
MacuHealth is a nutritional supplement leader. Our targeted formulas include MacuHealth for daily eye health, MacuHealth Plus for aging eye support, Vitreous Health for vitreous care, Vision Edge Pro for visual performance in athletes, TG Omega-3 for ocular and systemic wellness, and MacuHealth DM for eye and metabolic support. Call MacuHealth today and mention this podcast for special discounts. Experience the difference with MacuHealth. Nutrition you can see.
With more screen usage and indoor time, myopia, also known as nearsightedness, is increasing and getting worse in children. Now, certified eye doctors can prescribe MiSight One Day, the first and only FDA-approved soft contact lens to slow myopia progression in age-appropriate children. Visit CooperVision.com to find a Brilliant Futures certified eye doctor near you. Do your patients know what presbyopia is?
There are people who are afraid of the press.
Have you talked to your patients about multifocal contact lenses?
I've heard the bifocal, but not multifocal.
Do you need help with your multifocal strategy? Learn more at the conclusion of this episode.